If A is an n by n invertible matrix, then so is A transpose. True or false? True. That's part of the invertible matrix theorem. For the vector 2, 3, what are the associated homogeneous coordinates? Yes. 2, 3, 1. You just throw ones on there. We'll talk about it when we get there. This is like a computer graphics thing. If you want to change the location of a pixel, right, it has certain coordinates. And in order to make the programming easy, you can use multiplication by 3 by 3 matrices. So all of our coordinates have to be 3 by 1 vectors, and we just throw ones in that third entry just to make the programming work. Yeah, for that too. Yep. Yep. For the transformation, for the translations. Yeah. If a matrix transformation is both 1-to-1 and onto, the matrix is invertible. True or false? True. Yep. Also part of the invertible matrix theorem. So the invertible matrix theorem is just this list of a bunch of things that are all logically equivalent. So logically equivalent means if one is true, then they're all true, and or if one is false, then they're all false. And there's a little bit of notation that got messed up in my printing here. But so this is in your book, and it's also in on Moodle. There's a file called Caitlin's Reading Notes. So this is in there too. So notice that this only applies to square matrices. So this whole theorem only applies when you're dealing with square matrices. And we have a whole bunch of things that are equivalent. So invertible matrix, that means it can be row reduced into IN, which is the n by n identity matrix. And this one, we talked about last class because that's how you find an inverse matrix, right? You augment your matrix with the identity. And if there is an inverse, they swap. Well, the identity lands over here and a inverse lands on the right. And you can use that fact to talk about a lot of stuff, right? Because if you can row reduce into the identity, that means you have a pivot in every row and a pivot in every column, which means you have n pivot positions. And then all of these other things are things we've already talked about in chapter 1. It means the columns of the matrix are linearly independent, which is the definition of that is that the matrix equation AX equals 0 has only the trivial solution. It means that the linear transformation T of X equals AX is 1-to-1, and onto means that the solutions to AX equals B are unique. Yep. Oh yeah. It's kind of buried in that it's true that it has at least one, right? But it's stronger that it says to say exactly one. So I don't know why they say that. Like they're not wrong because it's true. If you have exactly one, then you do have at least one. So I don't know why they did that, but exactly one is stronger. So that's what I wrote. We can say that the columns of A span the whole space Rn. I already said onto. This is just the definition of inverse, right? And A transpose is also invertible. All right, so we're going to use this. The idea is if I ask you about one thing, you can find out the answer by answering any of these. So you do the easiest thing, and then you know the answer to all of these questions. Okay. Row reduce, and if you get the identity, it's all yes. If you don't get the identity, they're all no. Yes. Right. Well, if it's a square matrix and you have a pivot in every column, then you have to have a pivot in every row. Yeah. All right, so let's take a look at these four matrices. Two of them can be seen to be singular, that is not invertible. They don't have an inverse just by looking at them. So we have to think about what it means to not have an inverse. It means you cannot row reduce it to the identity. C, definitely, because we've got this column of zeros, right? So that means that those three columns are not linearly independent. So that means everything on the list is false. So it's not invertible. How about another one? B, the row of zeros does the same thing. Okay. It can't reduce to the identity because you can never get a pivot in that row. Okay, so B and C can't reduce, can't RREF to I, to the identity. All right. Which of these can you tell does have an inverse just by looking at it? That it will row reduce to the identity. How do you know A? Yeah, it's got the triangular thing here, right? So whether it's upper or lower triangular, that means it's in echelon. You could put it in echelon form and it will row reduce to the identity. Will be equivalent to the identity matrix. And then this last one, I have to do a little bit more work to determine if it is invertible or singular. Does it have an inverse or does it not? D. So I want to know, does it row reduce to the identity? So you would just put it in your calculator, hit RREF, right? And just RREF on calculator, and the answer is yes, they're equivalent. So it is invertible. Yeah. Nope, it's got it. Oh, I see. So, yeah, I guess you could rearrange the rows and make it the bottom left. Yeah, yeah. Yeah, because that's one of the things that's allowed for the row reduction algorithm is to swap rows. All right, if A is an n by n matrix and the transformation T of x equals AX is 1 to 1, what else can you say about that transformation? Or you can say A is invertible. Yep. And the transformation is invertible too, right? Because so a transformation is like a function. So this function or transformation has an inverse, so that's good. So T of x has an inverse transformation. Good, I didn't even think of that one. Is it onto? Yeah. Yes, if it's 1 to 1, it's also onto. It maps onto Rn, the codomain Rn. The columns of A span Rn. Yep, you can say that. Which is not something that you would say about the transformation. Right. It's you would say that about the columns of A. Yeah, it's just nitpicky language thing. I wouldn't mark that wrong if you wrote that. Okay, so last thing, I want to prove that if A is an invertible matrix, so A has an inverse, then A transpose has to also be invertible. All right, so what I'm given, A is invertible. Right, which means simply A inverse exists. right? And what I want to show, NTS is my shorthand for need to show, in order to prove that A transpose is invertible, I have to come up with some matrix that when you multiply it by A transpose, you get what? The identity, right? To show that a matrix is invertible, you have to find that matrix that you multiply by and you get the identity. So I need to show that there exists some matrix such that, let's call this C, some matrix C such that C times A transpose equals the identity, and also A transpose times C. No, A times A transpose is not necessarily the identity. Right. Transpose, where you make rows columns and columns rows. It's a different thing than the inverse. All right, so I haven't done any work trying to prove it yet. All I've done is sort of taken the statement and translated what do I know and what do I want to show. Okay, so to prove it, I'm going to start with what I know. A inverse exists, right? So we know that A times A inverse equals the identity. That's real, right? I know that for sure. All right. What I want to know has to do with the transpose of A. So I'm going to introduce some transposes somehow into this equation. I'm going to take the transpose of both sides. A inverse transpose has to equal I transpose. Transpose the two matrices on either side, you should get the same thing. All right, anybody remember the rule from, I think it was last class, how you take the transpose of a product? Switch the order, yeah. So this says that A inverse transpose times A transpose. What's the transpose of the identity? The identity, yep. All right, I'm done. Why am I done? I proved it. Let's go back up and look at our goal, right? Our goal was to find some matrix, sorry, some matrix that I could multiply by A transpose and get the identity. Have I found a matrix that I can multiply by A transpose and get the identity? Yeah. Take A inverse and transpose it. This is that magical C, right? That's my matrix that I can multiply by A transpose and get the identity. Technically, I should do this argument again where I write A inverse A equals identity, just to show that A transpose times C, the other order also gives you the identity, but we don't have to write it all out. All right, so that's it for the demo. I'm going to have you do the activities until probably 11:30-ish, and then we'll do the demo for 2.7.